Hi guys, welcome to the lesson of partial differential equation. So in today's class, we are going to discuss the principle of superposition, Wellposedness, and maximum principle. So here is the idea for a linear partial differential equation of order 2 having two independent variables x and y. So the linear operator LU is equals to a naught function of xy times u function of xy plus b1 xy ux xy and so on, right? So this is the idea of a linear differential equation. So in order to check whether a given differential equation is linear or not, we are going to satisfy these two conditions. We'll apply these conditions on the given equation and we'll check if these conditions are followed. Then we may say that the differential equation is linear. Otherwise, we will call it as nonlinear. So let's take an example. Let's say that we have the heat equation that is basically non-homogeneous heat equation. All right. And we want to check that either it's linear or not. So for that, we are going to apply these two conditions. That is, the first condition is L times C1U1 plus C2U2 is equals to C1LU1 plus C2LU2. So we have learned these before in the lessons of linear algebra in the topic of the linear transformation, right? So the idea is same here. So now the linear operator, basically these are the linear operators, right? Dawa squared or Dawa x squared, these all are linear operators. Dawa squared over Dawa x, Dawa y. So now we are going to check either this is linear or not. So we can say that if this is the equation, if this is the equation, that is Dawa u over Dawa t minus k times Dawa square u over Dawa x square is equals to function of xt. We can also write this equation in this form: Dawa over Dawa t minus k times Dawa square over Dawa x square times u, where this is a linear operator, right? So we can also recall the idea of the differential equations, the ordinary differential equations, where we write the equation. For example, if the equation was given like this, so we write it in this form: d squared y minus 2 dy plus y, and then we write it in this way. All right. So this is basically the linear operator. So it can be written as Ly. All right. So the idea is same here, and we will check some equations. We'll take some examples, and let's take an example. Dawa u over dawa t is equals to dawa u over dawa x whole squared. Now we want to check, we are saying that it's not a linear equation, and we want to check why it's not a linear equation. So we will apply the condition, that is L of Cu is equals to C times Lu. All right, so we will check this condition. What we will do, first of all, we can write the equation like this. Lu is equals to dawa u over dawa t minus dawa u over dawa x whole squared. Then L of Cu will be equals to dawa Cu over dawa t. What we are doing now, we are replacing this u with Cu, right? Because we want to check L of Cu. So Now you can check that this C is constant, so we can move it out. So it will be outside C dava U or dava T minus then there is a squared, a whole squared on this function. So when we will take this C out, it will be C squared outside. And now if you can take C common from these both, so we will take common C, and what we will left inside will be dava U over dava T minus C times dava U over dava X whole squared. So which is not basically equals to C LU because of this C, right? Because this C is here, so we say that this is not equals to C time LU, so this is not linear, right? So this is non-linear partial differential equation. And we can observe from this function that this is non-linear because these type of functions are non-linear. These derivatives are non-linear, right? And like in the case of differential, ordinary differential equation, this derivative was non-linear, right? So this condition is violated, and we can now take another example, and we are saying that check whether this equation is linear or not, right? So we are going to check, so we will apply the conditions. Condition number 1. So first of all, we can write this equation in this form, right? Taking U outside and only leaving operators inside, right? With the coefficients. So this will be LU is equals to this whole function is L, and here it's U. So LU is equals to f of function of x, y, z, and t. So it's basically a function of 3 independent variables. In fact, yes, this is the function of 4 independent variables. Yes, in fact, because of t, x, y, and z, there are 4 independent variables. All right, so now we can write L of u is equals to L of C1 U1 plus C2 U2 is equals to, because now we are supposing that by the principle of superposition, this U is equals to C1 U1 plus C2 U2, right? So now we will check. So this L times U will be equals to LC1 U1 plus C2 U2, because this U is now equals to C1 U1 plus C2 U2. So we will replace this U with C1 U1 plus C2 U2. And so we can write in this form by separating them. This will be C1 L times U1 plus C2 L times U2, right? Now we can write in this way. For every U, we will replace with C1 U1 plus C2 U2 everywhere in the equation, right? Everywhere. And after that, we can arrange the terms for simplification. All C1 U1s will be on one side, and C2 U2 will all the C2 U2s will be on the other side. Or no, just not do that, just do like this, that dava or dava t C1 U1 like this with dava over dava t C2 U2. Like arrange this with dava yes, this is the simplified form. This is dava over dava t times C1 U1. Here it's dava over dava t C1 U1, then dava over dava t multiplied by C2 U2. So here it will be dava over dava t C2 U2 minus, similarly for y, this operator will be multiplied by both C1 and C2 U2. So it will become like this, and for similarly for this operator, this will be the form, and for this operator here, this will be the form, right? After, now we will simplify it more. So we will put this C1 out. So we're left with dava U1 over dava t minus y times c1 dou y square u1 over dou x squared plus minus xc1 dou y squared u1 over dou y squared minus zc1 dou y square u1 over dou z square, right? So this is the these are the terms with the c1 u1, and now these are the terms with the c2 u2, right? So now we can take c1 as common here, so we can take it common, c1 outside plus then c2 outside here, and we can write the equation. Now we'll write in this way, L C1 L of U1, right? So what we'll do, we'll keep the operators inside. These are the operators, that is L times U1. Then these are the operators times U2, right? So now we will see that this is C1 times LU1 and this is C2 times LU2. So we can write here, this is C1 times LU1. This is C2 times LU2. So now we are done. We can see that this is C1 times LU1 plus C2 times LU2. So we are done with this condition. This condition is enough and this is good. This is satisfied. Now we'll apply the second condition. That is LCU is equals to CLU. For that, again, we will substitute CU everywhere instead of U. So we did here dawa CU or dawa T here, and in each of the derivative, right? Now we can see that we can move this C out of the derivative because this is constant, right? So for every derivative, we will do that. We'll move it out, right? Like this. So we'll get this form, right? Now we can take this C out, take the C as common because C is everywhere common. So we're left with dou u or dou t minus y dou y square u over dou x squared minus x times dou y squared u over dou y squared minus z times dou y squared u over dou z squared, right? Then we can write in the form of the operator that we know that we can take this u outside from all these operators, so we're left with the linear operators only, right, in the box. So now you can see that this is C times LU, and we started with LCU and we get to the conclusion that this L times CU is equals to C times LU, so condition 2 is also satisfied. It means that the equation is linear, right? So now we will talk about the Wellposedness. So the conditions for the Wellposedness are: a PD is said to be well-posed if the solution to the problem, number 1, exists, number 2, it's unique, and number 3, it's stable. So existence and uniqueness you already know from the ordinary differential equations. What did it mean? The existence means that the solution to the problem exists, right? So number 2 is the condition number 2 is saying that the solution is unique, right? Like we cannot get more than one solution. We will get only one solution. So we called it that is a unique solution. And the condition number 3 is stability, which means that stability means small changes in the data produce small changes in the solution, right? So if you will change our data a little bit, like if we'll change the boundary conditions or the initial conditions, then it should not produce a very large variation in the solution. So we will check in some questions that how it works. So let's do that. Now we will take a problem and we will show that what the stability means. So let's take the Laplace equation. This is Laplace equation, and this is also called the steady heat equation in 2 dimensions, right? So here are the boundary conditions. U of x comma 0 is equals to 0, and uy of x comma 0 is equals to 1 over n sine nx, right? And this is the solution to the given Laplace equation, right? So now we will check that if we make variation in the condition, so what will be its effect on the solution, right? So this is our goal, to check the stability. So we are saying that let's n tends to infinity, right? And now we want to check that what happens to the solution when n tends to infinity. So we now we can see that limit n tend to infinity for the condition will be 1 over infinity times sine infinity. So it will make this 1 over infinity 0. So this will be equals to 0, right? So here we can see that because sine infinity will always assume a value between -1 and 1. We know that because sine is always between -1 and 1, whatever value you put to the angle. All right, so then this will become 0. So 0 times any constant is 0, right? Then we will apply this to the solution, the same condition, that is n tends to infinity. So limit n tend to infinity for the solution. So limit tend to infinity, now we want to apply on this. So we can see that this is the sine hyperbolic ny is equals to e to the power ny minus e to the power negative ny divided by 2, right? So if we will apply the limit n directly on this function, what we will get is we will get indeterminate form, because it will be infinity in the numerator and again infinity in the denominator. So to avoid this chaos, we just want to apply the L'Hopital's rule to get the limit, right? So first of all, what we'll do, we will apply the identity for sine hyperbolic ny, that is equals to e to the power ny minus e to the power negative ny over 2. Then we will take these separately, this function with e to the power ny and minus this function to the with the e to the power negative ny, and we will apply the limit separately, right? So 1 over 2 is common. It will be, we can take it outside of the bracket, and now we'll apply the L'Hopital's rule. So you know the L'Hopital's rule, what we are doing, we are differentiating the numerator and the denominator, right? So when we will differentiate this function, we will get this n times e to the power ny sine nx plus n e to the power ny cos nx, right? Or, and then when we will differentiate this function in the denominator n square, so we will get 2n, right? So n is in the denominator and n in the numerator, right? So we can cancel out this with this, right? So negative limit n tend to infinity, and similarly differential for this function. All right, so the derivative of this e to the power negative ny sine nx will be equals to negative n e to the power negative ny sine nx plus n e to the power negative ny cos nx, right? And over 2n, because the derivative of n square is 2n, right? So similarly in this case also, this n will cancel out with these n's, right? Now we will left with e to the power ny is common in both, so we can take it outside. inside sine x plus cos sine nx plus cos nx over 2 minus limit n tends to infinity, and similar for this, right? So now we can apply the limits, right? So because there is no n in the denominator, so we cannot get any indeterminate form, right? So it will be the e to the power infinity. For n we will apply infinity, and for again sine infinity and plus cos infinity, this will again assume a value between -1 and 1, -1 and 1, right? So whatever we know that whatever value we give to the angle, we will always get a value between -1 and 1 for both cases, that is sine and cosine, right? And similarly here it will be also the same. So now we can see that this is e to the power infinity, so it is actually infinity, and this e to the power -infinity is 0, right? So e to the power infinity is infinity, e to the power -infinity is 0. So here we go. Here we can see that this infinity is multiplied by this function, right? So it will make it infinite, and this 0 times this function will be 0. So half times infinity will be infinity. So now we can see that when n tends to infinity, this part uy of x comma 0 converges at 0, right? But the solution diverges to infinity. So now you can see that it's like big deflection, right? It's going to 0 and it's going to infinity, so it's a large variation. So we'll say that this problem is not well posed, or we can say that this problem is ill posed. All right, so this is the idea of the well-posedness and ill-posedness. We can say that by changing the condition, the solution is changed, and there is a big variation. The condition is converging to 0, but the solution diverges to infinity, right? So now we are going to discuss the maximum principle for partial differential equations. So the idea is very clear that the maximum principle states that for a non-homogeneous, for a homogeneous heat equation or a partial differential equation, the maximum and minimum can only be occur on the boundaries. So it cannot be occur in the interior, right? Now we'll solve some examples that how to find maximum and minimum for the equations. We will take some examples and we will see that. So let's take a question for the maximum principle. Let's say that, just a minute. So here is an example of a homogeneous heat equation. Ut is equals to uxx, and the conditions are given as 0t is equals to 0 and u of pi comma t is equals to 0, right? Then u of x comma 0, that is the initial condition, is equals to sine x plus 1 over 2 sine 2x. Now we need to show that the maximum, and we also, this x is between 0 and pi, right? So now we need to show that the solution satisfies this condition, right? 3√3/4. So it means that the minimum value of the solution will be 0 and the maximum value will be 3√3/4. So now we can use some calculus here. We know that the maximum of function, maximum or minimum, we can say that maximum or minimum of a function is where the slope is 0, right? So now we can use initial condition because we know that the solution of this heat equation will be derived from this initial condition, and the initial condition plays a big role. All right, so now we can see that the condition is given as u of x comma 0 is equals to sine x plus 1/2 sine x. Oh, sorry, 1/2 sine 2x, right? So now to find the slope, we will differentiate this equation. So ux will be equals to cos x plus 1/2 times 2 cos 2x, right? This will be cancel out. So ux will be equals to cos x plus cos 2x, right? So now we know that we can write for this cos 2x, we can write it like this: 2 cos square x minus 1, right? And or we can simplify it like this. Let's use this identity: minus sine square x. So it will be the same. I think we'll get the same result that I wrote before, because this sine square x is 1 minus cos square x. So it will be 2 cos square x plus cosine x minus 1, right? So by breaking the middle term, we can write it like this: minus cos x minus 1, right? So 2 cos x is common here. We will left with cos x plus 1. Minus 1 is common here. We will left with cos x plus 1 inside the bracket. So this will be 2 cos x minus 1. This will be cos x plus 1 equals to 0, right? So we need to find the maximum. So that's why we put equals to 0. So either 2 cos x minus 1 is equals to 0, or cos x plus 1 is equals to 0, right? So this will be 2 cos x is equals to 1. Cos x is equals to -1. So x is equals to cos inverse half, and x is equals to cos inverse -1. All right, so we know that cos inverse half is equals to 60 degrees. So we can write x is equals to pi over 3 for cos 60. We can use this pi over 3. And then cos inverse 1 will be equals to, sorry, cos inverse -1. So it's pi. All right. Cos inverse -1 is equals to pi. Now we can put these values for x is equals to pi over 3 u of pi over 3 comma 0 will be equals to sine pi over 3 plus 1 over 2 sine 2 pi over 3. So sine pi over 3, that is sine 60 degrees, will be equals to square root 3 over 2 plus 1 over 2 times sine 2 pi over 3, that is sine 120, is also equals to square root of 3 over 2, right? So this is equals to square root of 3 over 2 plus square root of 3 over 4. So this is 2 square root of 3 over, sorry, plus root 3 over 4. So this is equals to 3 square root of 3 over 4. All right, so this is the maximum value what it will get, because it's given in the question that it should be equals to or less than this, right? So we found the maximum, now we will find the minimum. So we'll apply pi, sine pi plus 1 over 2 sine 2 pi. So we know that sine pi is 0, sine 2 pi is also 0. So u of pi comma 0 is equals to 0, right? So we came to the conclusion that the solution ux comma t will be always between 0 and 3 square root 3 over 4 heads u. All right, so this is the maximum and minimum principle for the partial differential equations, and you can find this way the maximum and the minimum, right? So you can take more examples on the maximum and minimum principles. Hope you guys will learn from this lecture. These are important topics for partial differential equations to study the qualitative qualitative solutions of partial differential equations, the behavior actually of the partial differential equations, right?